Hey everybody, I hope you're doing well and miss you all, and I hope to see you next week. We're going to be entering the home stretch here, and our final unit is going to be all about optics, one of my favorite things ever. Optics has a whole lot going on in it, and we're going to be focusing on reflection and refraction of light. But there's much more happening in optics that we can talk about. So, what is optics? Well, optics is typically about ways to manipulate light. So we're going to be reviewing a little bit of light stuff and look at some phenomenon, specifically reflection and refraction. But there's so much more that you can do with light: polarization, diffraction, interference, holography. Those are, especially holography and interference, some of my favorite things to talk about with light. So let's get right to it. There's a video clip here in the slides that you should look at if you get some time. It's about a 10-minute clip from the Slow-Mo guys, and they visit a lab at Caltech where they have found out a way to film light. It is amazing. There's just so much going on there that I don't want to just give you like the 10-second version. I really want you to check that out on your own. So you can't see it linked from this particular video, but if you go into the slides, it's there's a YouTube link there. So check it out. It is fantastic. Plus, there's a making of that's kind of cool. But the first video is remarkable. Okay, so let's think about what light is. It's an electromagnetic wave. If you remember, electromagnetic waves are typically represented on a spectrum, and generally we break them down into 7 major categories: radio waves, microwave, infrared, visible or Roy Biv, ultraviolet, X-rays, and gamma rays. And that list goes from low frequency to high frequency. All of these EM waves travel at the speed of light in a vacuum, of course. However, if they change mediums, then their speed will change. And in fact, the extent to which they change does depend on the wavelength of the light. We'll get more into that the second part of this unit, but first we're going to talk about what happens when light stays in the same medium but hits something that allows it to bounce off of. And that phenomenon is called reflection. So reflection of light, as I just said, is light bouncing off of a reflective surface. Normally we think of that as being a mirror, but it can really be anything that's relatively bright. A white wall, for example, glass, for example. We're going to mostly be looking at mirrors, and all mirrors are things that are generally coated. Well, historically they've been coated with silver or gold, but that stuff's expensive. So generally speaking, they get coated now with aluminum or something that's fairly plentiful and cheap. Here's an example of reflection happening with a billiard ball. So they're going to hit the cue ball, and it's going to bounce 2 times and until it goes into the side pocket. Now watch the second time this GIF comes up, and you're going to see they put a little light in here, and it bounces at various angles. And excuse me, how billiards bounce, and indeed how something like this bounces, these balls here that are programmed to bounce elastically. Do that again. How they actually bounce, it obeys a type of conservation law. Now for light we call this law the law of reflection, but when we're talking about things like balls, we generally refer to the law of conservation of momentum and conservation of energy, but particularly the conservation of momentum, which we don't generally get into too much in the first year physics class. So here's a little air puck that is bouncing off of a wall. I'm going to put in a little bit of geometry here. And this dotted line represents the path, the initial path or the incident path, and that is the reflected path. And I put in a normal or perpendicular line here, and I think you can easily tell that these angles seem to be about the same. Or if we look at it here, we're starting to see that there is a pattern. When light hits a reflective surface, it bounces off in a very predictable way. Or here. So light is going to come here, it's going to reflect off of the surface in red, as you can see, and it bounces off at the same angle. Now, of course, these GIFs are suggesting that it's slow, and in fact all this action happens at the speed of light, way too fast for you to perceive. Now, something like this, that's something you can actually perceive, but light, of course, is happening. These interactions or bounces or collisions are happening at the speed of light. So, what is this so-called law of reflection? Oh, it's really simple. In fact, you've already seen it in the laser lab. Reflection is light bouncing off a reflective surface, and it does obey a simple law, the law of reflection. Angle in equals angle out, or if you prefer, angle of incidence, that's this, equals the angle of reflection. Incident ray, reflected ray. Pretty straightforward if you think about it. You can look at 3 different types of reflection, but they're all really the same. Standard mirror reflection is what I've been talking about so far. Angle of incidence equals angle of reflection. Specular reflection, you just have more than one ray. Those rays are parallel to each other. They hit parallel and they emerge parallel. And the more complicated example really isn't complicated at all, but it sure looks it, and that's diffused reflection, which is what happens when you get light hitting some jagged or irregular or almost broken surface. It'd be kind of like if you have light that's hitting a like a multifaceted diamond ring, or a multifaceted cubic zirconia, or more likely if it's hitting some glass, if it's hitting rippling water, light that's hitting an irregular surface, maybe even hitting a disco ball, a mirror ball like the one in my classroom, something like that, then the light bounces off in many different directions, and it doesn't look like it's obeying the law of reflection, but each individual ray, even in this picture you can see it, each individual ray is obeying the law of reflection. Here it is kind of 3D-ified. Angle of incidence equals angle of reflection. Here's something that I think you're going to be playing around with. It's a really pretty simple ray optics simulation. How this works is you can choose a single ray light source, and ta-da, that's it. And if you want, you can actually go down here and you can go into to simulate colors, and that actually allows you to change the wavelength, which is tons of fun. Each of these things happens to be a Mach laser beam. And then you can have another light source like so. Go to up here to mirrors, and then mirror segments are what you think they are. They're basically flat mirrors, so they're actually reflective on both surfaces. Like so. If you want, I'm going to undo this. You can also use beams, which are like that, which are kind of cool. Now, you don't want to just use flat segments. You want to use either parabolic arcs, parabolic mirrors, or circular arcs. Let's start with a circular arc. These are a little bit tricky to kind of tame. You kind of have to make them small, and then you spread them out. And then it gets really cool, like so. Undo that, and if you want to try something more interesting, you can also try parabolic, which is a little more complicated. Those of you who speak mathematics probably know what parabolas do, and in 3 dimensions what paraboloids do. In fact, satellite dishes are not just parabolic, they're paraboloidal. Radio telescopes, and in fact all telescopes that are reflecting telescopes, are paraboloids. So I hope you have a chance to play around with this. In fact, I think I actually wrote it into one of the virtual labs that you will have to play around with it and create some pretty cool stuff. Again, another image showing you the angle of incidence equals the angle of reflection. So let's talk about something that is related, but maybe a little bit strange. I know you've looked in full-length mirrors before, so this begs the question, how tall does a full-length mirror have to be so that you can see your entire body? The obvious supposed theoretical answer would be, well, it's got to be the height of your body. Or you might even think it also depends on how close you are. The closer you are, the closer you are may make a difference as to how much of your body you can see. So, is that actually true? Well, let's take a look in closer detail. So here I have a woman who's standing close to a wall, and there's a mirror, and you can tell, it kind of cuts to the chase immediately, there's no longer a surprise. You can tell the mirror does not have to be her height in order that she can see her entire body. It's got to be just about half her height. Now, why is that? Well, first of all, it does have to be flat against the wall. That makes it a little bit of a limited problem. If you put it at an angle, then it's a slightly different problem, although the rules are, of course, the same. For her to see the top of her head, she has to have her eyes located right there with relative to the mirror, and so you can see the top of her head. That is a law of reflection problem. Now, to see her feet, you notice that the light bounced off her feet up there and over there. So that works out to be about half her height. Now, I'll demonstrate this in class, and I think you'll be really surprised. I think the more shocking thing is that the distance away does not actually matter one bit. It's the same result whether she's close or whether she's far away. How far that she is away makes no difference whatsoever. If you want to be able to see yourself in a full-length mirror, the full-length mirror does not have to be full height, but rather just over half your height. So, Now, let's imagine looking at yourself in a bathroom mirror, like one of the bathroom mirrors here at school. Those are kind of longer width mirrors. If you want to be able to see yourself in a bathroom mirror or a plane mirror, well, that's pretty easy. You just have to be able to look into it and be in front of it. This is an overhead view, by the way, kind of like if you were on top of the bathroom ceiling, and that would be the wall / mirror right there. So you can see yourself as long as you're standing between these two dotted lines. You can easily see yourself in this range. You move over here, no, you're not going to see yourself. Move over here, you're not going to see yourself. Move way back here, you'll still see yourself as long as you are within the confines of the mirror. But how about another person? If you're standing there, where can somebody else see you? They can see you anywhere else the law of reflection allows it. So you draw a line from there over to there, they will be able to see this entire range that's described with this dotted line. That's a huge range. And in fact, if they move back further, this goes further, they can actually see you way back. So they can see you anywhere that the law of reflection allows it. Now, that's not the only thing. In fact, you can see them as well. They can see you and you can see them. You might have even seen side view mirrors on big tractor trailers where it says something like, warning, if you cannot see me, I can't see you, or something to that effect. So yes, in fact, if you can see them, they can see you, and vice versa. So again, much bigger range for you. Now, if you change where you're standing, so again, this is just you being further back. It's the same thing, except the geometry makes it a little bit different, not quite as deep. That's a little bit, or I'm sorry, not quite as wide a range. Let's say you're standing over here. Nobody can see you in the mirror by looking that way. Not a chance. But anybody standing anywhere in this dotted range here can see you, and you can see them. All right, so the next thing we're going to be talking about are curved mirrors, and specifically concave and convex mirrors. This is where the physics starts to get a little bit more confusing. It's not really hard, and it's not any different, but because the surfaces are curved, that makes it seem a good bit stranger. So in the lab that you did with the lasers, you probably saw something kind of like that, and you might have even seen something like this in the virtual lab. And that is a convex mirror. Look at the difference between the concave mirrors where the light is all brought to this point, and a convex mirror where it's all kind of emanating away, and never, these rays only diverge, they never touch each other. You can imagine that they come back from a common point back here. But let's go back here for a moment. This point is where all these rays converge, and these rays right here are parallel, so they do converge at a point. We're going to see with rules of mirrors that it gets a little bit trickier when things don't have parallel rays going from them, which is normally the case. In fact, parallel rays are kind of unusual, more of an aberration. Convex mirror again. And which is always if you have both at the same time. Okay, so what is a curved mirror? A curved mirror is kind of like a flat mirror. You can almost imagine a flat mirror that's flexible and that you are bending it. A curved mirror, in this case a concave mirror, is kind of like an infinite number of very tiny flat mirrors connected to each other in a curved shape. So I really have this kind of crude here. I think I just drew in 7 flat shapes, but this would mimic a curved mirror. Not very well for 7, but the greater the number of tiny flat mirrors you have, and as long as they are arranged in the right mathematical shape to depict either a parabola or a circle, you're going to get a curved mirror effect. So basically all a curved mirror happens to be is just a huge number of itty-bitty flat mirrors that are in the right geometric shape. Actually, let me show you one other way to think about this. So I'm going to kind of imagine putting a number of a polygon inside. So there's one-sided polygon. It's not really a polygon until we get to 3 sides. Okay, so this is a 3-sided figure, a triangle. Note that the perimeter of the polygon here is 36.37 units. The circumference circle that goes with that is 43.9. But watch what happens to these numbers, the perimeter of the triangle or the perimeter of the polygon, and look how much closer it gets to the circumference. When I go up to 5, it's now 41.1 to 43.9. If I go up to 7, 42.5 to 43.9. Let's go up to 12, 43.48 to 43.98. And by the time we get to 20, it's a perimeter of 43.8 to 43.98, and it's almost indistinguishable from a circle. So in other words, the greater number of sides you have, the closer it gets to approximating a curve. Okay, more to come.